Okay, so hello and welcome everyone, and thank you for joining our webinar today. My name is Catherine, and I'm one of the data scientists at the evangelism team here at KNIME. And I'm here today together with Rosaria Silipo, who is the head of our evangelism team. And together we want to give you today an introduction to deep learning, and we want to show you how you can use the Keras integration of KNIME Analytics platform to define and train your deep learning models without writing any code. Before we get started, a bit of housekeeping. Please use our Q&A section to post your questions and to upvote questions or to upvote your favorite questions so we can answer them in the end of the session. For your information, the session is recorded and will be available afterwards on YouTube in case you want to rewatch it. And after the event or after the webinar, we will send out a follow-up email, including the slides which we are using today with all the links and promotion codes that we share throughout the session. To ask your questions, you can just click on the Q&A button in the Zoom toolbar. This will open a new window for you where you can then type in your question or upvote the questions from other attendees. The webinar today is kind of split into two parts. I will talk now in the beginning a little bit about the basics behind neural networks and deep learning before I hand over to Rosaria, who is going to introduce the concept of convolutional neural networks. So let's start with the basics behind neural networks and deep learning. And I would like to start really simple with the simplest neural network or deep learning model, which is not deep yet at all, which is just a single neuron. And historically, the single neuron, or how we model a single neuron, is motivated by a biological neuron. And a biological neuron always has some inputs, a cell body, and some outputs. And based on the inputs, the cell body decides whether the output or the outputs are active or inactive. And if we want to model such a single biological neuron with an artificial neuron, what we have as well is some inputs and some outputs. And we have a cell body where we have some weights, which are here W1 and W2, and a bias, plus an activation function. And how do we calculate now the activation? So what we normally do here is we take the weighted sum of our inputs. This means what we calculate is always we take each input and multiply it with the corresponding weights and sum these values up, and we add a bias. This means in this case, we calculate x1 multiplied by w1 plus x2 multiplied by w2 plus a bias value. And then we add in addition an activation function where we can use, for example, the sigmoid activation function, which has values between 0 and 1, which makes it really nice to interpret it as a probability. And if we then, and this single neuron is actually the basic or the smallest building block in each neural network or deep learning model. And in a neural network, in a biological neural network, we then connect many of these single neurons together. And one way of how we can model a neural network or an artificial neural network is by connecting them in the way as we can see here on the bottom right, which we call a feed-forward fully connected neural network. And in this case, we have an input layer here and an output layer Y, and we have two hidden layers in between. And as you can see, the hidden layers or this neural network in general is just a connection of many of these different smallest building blocks of neurons. And how this works here is that we have an input layer and we use the inputs to calculate the activations in the first hidden layer. And then we use the activations from the first hidden layer to calculate the activations in the second hidden layer. And then the activations from the second hidden layer to actually calculate the output. And here we really always take the weighted sum of our inputs, and then we apply an activation function. And I mentioned already one possible activation function, which is the sigmoid function, but this is actually not the only used activation function. There are many other frequently used activation functions, and here on the slide you can see two more. We have on one hand, on the left-hand side, one more time, the sigmoid function. As you can see, it has values between 0 and 1 and has this S shape. But another frequently used activation function is the tanh function, which has values between -1 and 1, and also this S-shaped function. Another often used activation function is the so-called rectified linear unit, or ReLU for short, which is 0 if we have a negative value as input. This means if the weighted sum is negative, and otherwise we have the identity function. And what I would like to do now is I would like to show you how you can use a feed-forward neural network to solve a binary classification problem. And the binary classification problem I picked is that we want to train a feed-forward neural network to predict whether a person is going to pass our KNIME L1 certification or not. And as inputs, we have two inputs. We have the number of minutes a person attended our course and how many workflows a person has built in the past. And then we have the label information, whether this person passed or didn't pass. And I visualize this here on a scatter plot. And I can use now this labeled historical data to train a feed-forward neural network to predict for a new person whether this person is going to pass our L1 certification based on the information, how many minutes this person attended our course and how many workflows this person built in the past. And a really simple feed-forward neural network that I could use for this task is that I define a neural network with one input layer with two inputs for my two input features, the minutes attended and the workflows, the number of workflows a person has built. We have one hidden layer where we use the activation function TANH, and one output layer where I use the activation function sigmoid, because the output of this neuron I can then interpret as the probability that a person has passed our L1 certification or not. And then I have in my neural network all the weights which I need to calculate the activations in the hidden layer and in the output layer. And if I have a neural network like this, then I could use this neural network now to predict for a new person whether this person is going to pass the exam or not. And I want to do this now for an example person who has attended our course for 170 minutes and has built 8 workflows in the past, which would be somewhere around here, where all people actually have passed the exam. So I would expect my network to predict that this person is going to pass. So let's feed this information in our network. What we normally do before we feed this information in our network is that we normalize the inputs. And that's what I want to do here as well. And I decided to use here a min-max normalization where I normalize my values between 0 and 1. So we take the normalized values and feed them into our network. And now we can use the different weights and the TANH activation function to actually calculate the activations in the hidden layer. And with these activations in the hidden layer, we can move on to calculate the activation of our output layer by taking again the weighted sum. This means I multiply this value here, the activation with the correct weight, and the same for the second input, add the bias, and then apply the sigmoid activation function. And here I get now a probability of 0.013. And that might make you think, that's strange. We actually would expect that this person would pass because the person attended for 170 minutes and has built 8 workflows already. And the problem with this network is that we haven't trained this network. This means we need to train our network first to have here meaningful weights. And what you can see here are just some random weights that I picked. And the question now is, how can we actually train our network? And training our network means finding good weights. This means finding weights that actually lead to the correct predictions. And to do so, we always have to tell our network how good does it perform with the current weights. And therefore, we can use different error functions, which normally depend on one hand on the predicted value, which depends on the inputs and the weights, and the true value. And for a binary classification problem, what we can use is, for example, the loss function binary cross entropy. If we have a regression problem, we could also use, for example, just the squared error. And we tell now the network how good did it perform with the current weights, and based on this error, the network can then update the weights. And I will talk a little bit more how the weights are updated in a second. What we would do now is here we take into account just one training sample, but actually we don't want to find only good weights for one training sample, but for many training samples. That's why when we look for good weights, we don't take into account only one training sample, but we actually take the sum of many training samples. So we define a loss function, which is the sum over the error for many training samples in our training set. if we have, and how can we now find actually the weights which lead to the correct predictions? We find them in a way that we minimize this error function here. And for a really simple neural network where we have only two weights, we can actually visualize this loss landscape like we see here. So here we have an error function which only depends on two weights. And our goal here would be now to find the weights W1 and W2, which lead to the global minima in this loss landscape. And to do so, we can use the approach of gradient descent. Sorry, that's the wrong direction. And the idea behind gradient descent can be compared with someone going cycling under foggy conditions, where a mountain cyclist went up a mountain and now he wants to get back to the valley, but he actually can't see the valley because it got really foggy. And what an approach the mountain cyclist could use is that he starts at the current position, and until he reaches the value, what he does, he always looks into the direction of the steepest ascent, and then decides, okay, if this is the direction of the steepest ascent, then I move into the opposite direction, which is the direction of the steepest descent, and I cycle into this direction for 2 meters. And then I do the same thing again. I look again for the direction of the steepest ascent, and I cycle into the opposite direction for 2 meters. And I continue doing so until I reach the valley. And once I'm in the valley, I can return the positions of the valley. And that's exactly the steps which we perform also when we apply gradient descent to find the minimum in our loss landscape. And here we start with some initial weights. So that's the current position of the mountain cyclist. And until we reach the minimum, what we always do is we calculate the gradient with respect to the weights. That is the direction of the steepest ascent. And then we make a little step into the opposite direction, which is the steepest descent. And we continue doing this until we reach the minimum. And once we reach the minimum, then we can return the weights. And these are the weights that we then use in our trained neural network. We can also visualize this algorithm. So what we do is we always calculate the gradient, which is just a vector where we have the partial derivatives with respect to all of our weights. And then we take the opposite direction and we make a small step into this direction. And we continue doing this until we reached the valley. And then we return the weights which define the valley. What we haven't talked about yet is how we can actually calculate this gradient, because we need to calculate this gradient for each update of our weights. And this can be quite cost intensive. And an efficient way to calculate the gradients during this optimization process is called backpropagation, which is used during the training process of neural networks or deep learning models. And here we normally have two steps. We have always a forward pass and then a backward pass. And during the forward pass, we apply the current weights, and then we backpropagate the arrow through our network so we know how we need to update our weights. And mathematically, this is done by using the chain rule so that we can split the calculation of the partial derivatives, which we need in the gradient, into different parts. And for example, if I want to calculate for this simple network, the partial derivative of my loss function with respect to W2, I can use the loss function and split this into calculating the partial derivative of my loss function with respect to y hat, my output, multiplied by the partial derivative of my output with respect to W2. And if I then calculate also the partial derivative of my loss function with respect to W1, I can reuse parts already because, again, I can apply twice the chain rule so that I have, for example, the partial derivative of my loss function j with respect to y hat, which I calculated beforehand, so I can reuse it also here in the calculation of W1, of the partial derivative with respect to W1. And once I trained my network, then I have actually weights which do lead to the correct predictions. Also in my example, here we see now again the same network as before, but not with the random weights which I used, but the weights which I got after training my network. And if I now do the same with my input, so I input for the number of minutes, my 170 minutes, and for the number of workflows the person has built 8, in a normalized way into my input layer, and I calculate based on this input the activations for my hidden layer, and I use them to calculate the activation in my output layer, I actually get a probability of 0.967, and then I would actually hopefully predict correctly, or not hopefully, but I would predict correctly that a person who attends the course for 170 minutes and has built 8 workflows in the past actually passes our L1 certification normally. The loss landscape, which you saw in the beginning or earlier in my slides, was actually a quite simplified version, because actually the loss landscape for a real neural network looks much more complicated. And here on this slide, we can see the loss landscape of a real neural network, which I took from a paper where you can find the source here in the slides. And what they did, they tried to visualize the loss landscape of a real neural network where you have normally hundreds of weights, but they did some dimensionality reduction so that they can visualize it just based on 2 dimensions. And as you can see here, we have many different local minimas in this loss landscape. And finding here good weights is actually not so easy anymore with all these local minimas. And here, a really important setting option is actually the step size, which is also called learning rate. So how big do I make these steps into the different directions? And researchers have developed many different optimizers where we don't have to select this learning rate manually, but where we have adaptive learning rates, which change, for example, for the different partial derivatives, or also which change during the learning process, that we have bigger learning rates in the beginning, and then they decrease during the training process. And available optimizers that we have in the Keras integration of KNIME Analytics platform are, for example, ADAGRAD or ADAM, which uses an additional term during optimization, which is called the momentum term. Other important setting options that we have in a neural network or training options, settings for training a neural network that we have are the batch size and the number of epochs. And the batch size defines how many samples we actually take into account if you make one weight update. Because normally when you train a neural network, you have really a lot of data, and then always calculating the gradient on the whole data set is really expensive. So therefore, what we can do instead is we always take into account only a batch, so only some of the samples, and we update our weights already. And how many samples we actually take into account for each update is defined via the batch size. Another important setting is then the number of epochs, and this defines how often we use each training sample in the training process. A question that I get quite often is how can we define or how can we decide about the structure of the neural network or the architecture of our feed-forward neural network? And here you have a lot of different options that you can optimize. So for example, how many layers you use and how many neurons you use in a layer. But where I can give some tips is how you can decide between the loss function and therefore also for the activation function in the last layer. For example, for the binary classification problem I just introduced, we can use as loss function the binary cross entropy. And if we use binary cross entropy as the loss function, then I would suggest, or I recommend, to encode the 2 classes that we have in a binary classification problem as 0 and 1, and use as the activation function in the last layer sigmoid with just 1 unit. That's what I also did in my feed-forward neural network. In case of a multi-class classification problem, you would use, or you can use as loss function the categorical cross entropy. And in this case, I would use in the last layer softmax as the activation function, and the number of units here must be then equal to the number of different classes that you have in your multi-class classification problem. And in case of a regression problem, you can use, for example, the mean squared error or the mean absolute error as loss function. And here I would use then in the last layer as activation function either linear, if your regression problem can have positive and negative values, or if your regression problem can have only positive values, like for example, you train a network to predict house prices, then I would use ReLU as activation function. Remember, ReLU is 0 for negative values and the identity function, so like the linear function for positive values. We now think about what do we need to define if we define a feed-forward neural network. Then first of all, we need to define the structure which we want to train. This means how many layers, and for each layer, how many neurons this layer should have and which activation function. In addition, we need to define a loss function, and we need to select an optimizer and define settings like, for example, the number of epochs we want to train and also the batch size. And I now want to show you how you can use the Keras integration in KNIME Analytics platform to define all these things, to define a feed-forward neural network. So let's switch to KNIME Analytics platform. Here I prepared a little data set for the example which I just introduced in my slides, where I have the information, how many workflows a person has built in the past, how many minutes the person has attended our course, and whether this person passed or did not pass. And I perform here already some pre-processing, like for example, encoding the two classes into 1 and 0. So I say passed is encoded as 1, not passed encoded as 0. And then I create here different subsets, one for training, one for validation, and one for testing my trained network afterwards. And I normalize my data on one hand, the training data, and I apply the same normalization also on my validation and test. And now I would like to define the network structure of my feed-forward network, which I just introduced also in my slides. And therefore, I can look for the different Keras nodes. And the Keras integration comes with many different layer nodes on one hand, which you can see here. And on the other hand, also a Keras network learner and a Keras network executor node. The Keras network learner node allows us to train a network, and the Keras network executor node allows us to then apply a trained network to some new data. If I want to define the network which I want to train, I can use the different available layer nodes. And the node which I always need in the beginning is the Keras input layer node, which allows me to define my input. And to define the input, I can just open the configuration window and define how many inputs do I have. And in our case, we have 2 inputs. We used a fully connected feed-forward neural network in my slides, and therefore I need a layer which connects all neurons to each other in the different layers. And this is something that I can implement with a Keras dense layer. So I can add the next layer and say, okay, next I have a Keras dense layer, and I connect this one with my input layer. And in a Keras dense layer, I can then define again how many units I want to have. And remember in my slides, I had 2. And I can also select between the different available activation functions. And here you can see, for example, the tanh function, but also the redo function, linear, or the softmax function, which I mentioned earlier. I want to rebuild the network from my slides. That's why I select here tanh. And then I add a last layer, which is the output layer in our case, which is another dense layer, where in this case, because it's a binary classification problem, I use in the last layer just 1 unit, and I use as activation function the activation function sigmoid. Once I have defined my network and I have my training set ready, I can train this neural network, and therefore I can use, as I mentioned, the Keras network learner node. And into this node, I can feed on one hand the defined network, and on the other hand, the training set, and also some validation set, so that I can monitor how good does my neural network perform on some data that I don't use in this gradient descent update to see whether my model or my neural network starts overfitting, for example. In this Keras network learner node, I can also define things like the loss.
Catherine, can you please zoom on your screen?
Oh, sorry. Yes. Okay. Going back to the Keras network learner node, I hope it's better now. In the Keras network learner node, we can, for example, define the loss function which we want to use. But in addition, we can also define here which are our input features and where do we have our target feature. And then here we can select between the different loss functions. And as we have a binary classification problem at hand, I can use binary cross entropy here. In the options tab, I can define then the different training options which I mentioned. For example, the number of epochs, where I could use 120, for example. and I can define a training batch size and a validation batch size. In addition, we have here then the different optimizers, and I will use now, for example, ADA. Once I'm happy with my settings, I can click OK, and I can start executing. And as I mentioned, while the network is executing, I can also monitor how the loss changes over the different epochs and the different batches. And I can do so in KNIME by right-clicking the node while it's executing and selecting View Learning Monitor. And here I can see now in red how the accuracy changes on the training set, and in blue how the accuracy changes on my validation set. And I can switch to the loss tab to see how the loss changes over the different epochs and batches on my training set and on the validation set. I will stop learning here for now because I have executed this already ahead in time. And once I trained my network, I can then apply it to some new data with this Keras network executor node, where I can select again the columns which are the input, and I can define what should be my output. And in this case, I want to output the output of my sigmoid layer. That's what I do here. So I get as output the probability that a person will pass or not. And I can use this probability then to transform it into a prediction, checking whether the probability is above or below 0.5, and can then evaluate my model or my neural network. And in this case, my neural network did reach an accuracy of 92%. With this, I hope I gave you a little bit of an intuition how neural networks are trained and how you can define a neural network in KNIME Analytics platform using the Keras integration, as well as how you can train it using our Keras integration. And with this, I will hand over to Rosaria, who is going to show you how you can train deep learning models using the concept of convolutional neural networks.
Okay, hi. So Catherine, I left some questions for you to answer in the question and answer. So I hope I don't have the demo, so I hope my screen is going to be big enough. So in the second part of the webinar, we are going to move from the classic neural networks that Catherine has introduced to deep learning neural networks. So what makes and a classic neural network, a deep learning neural network. So there is the first attempt about the deep neural networks was about the number of hidden layers that a neural network can have. So I don't know how many hidden layers does a deep neural network need to have. I don't know. It's a question that is always asked, and you can try to find the answer. So anyway, that was the first attempt, and it was just referring to classic feed-forward neural network. Under the umbrella of deep learning, though, there are a number of new architectures and new paradigms that are more interesting than the number of hidden layers in a feed-forward neural network. So these new architectures and new paradigms, one is the convolutional layers for image classification. And this is what we will see in the second part of the webinar. The other one are recurrent neural networks for the analysis of sequential data. And this one is what we will see in the next webinar on April 20th. And then there are the generative adversarial networks and the transformer networks, but we will not describe them neither here nor in the next webinar, maybe at some point eventually. Okay, so as a concrete example for the second part of the webinar, we are going to deal with the MNIST dataset. The MNIST dataset contains images, and those are images of handwritten digits between 0 and 9. So this is an example of the kind of pictures of images that you have in this dataset. The idea is to classify these images and associate to each image its number, so the number that is in there. So since those are images, images are numerically represented as a matrix, and each cell of the matrix is a pixel, and each pixel contains the level of gray if we talk about a black and white image. So if in a black and white image, we are going to see that this image is going to be represented as a matrix of pixels containing 0 for a black color and containing 1 for a white color, and then between 0 and 1, all the shades of gray. For a color image, things don't change much, but instead of having one single matrix with level of grays, we are going to have 3 matrices according to the red, green, and blue framework. So these 3 matrices contain each the level of red, the level of green, and the level of blue. The combination of these 3 colors gives you the the actual color of the pixel. So the only difference between a black and white image and a color image is that you move from one single matrix representing the pixel configuration to 3 matrices, so a tensor of 3 matrices representing the color pixel. Okay, so let's talk now about convolutional neural networks. They got inspired by the organization of the visual cortex in the human brain. In the visual cortex, you have a bunch of neurons, and these neurons are responsible for a specific area of your visual field. This array of different neurons, then it becomes an array of exploration of the different areas in the visual field, and they cover the whole visual field. If they work, they cover the whole visual field, and they are responsible for extracting information, each one from its own visual, from its own area. So we take inspiration from these kind of neurons, and then we build an array of neurons, each neuron responsible for a portion of the input image. So the idea is that each neuron has a kernel. The kernel is a mask that overlaps onto a portion P of the image. The pixels in the portion P are convoluted together with the values in the kernel K. The result of this convolution operation is the output of the neuron. Then what happens? We start from the first neuron. The first neuron overlaps the mask onto the portion P, onto the dedicated portion P of the image, calculates the convolution, produces the output. Then we move to the second neuron. The second neuron moves the kernel a bit, let's say, to the right. Again, overlaps the mask onto the new portion P of the image, calculates the convolution, produces the output, and so on. And the third neuron, the kernel gets moved a bit more. Again, the overlapping, again, the convolution, again, the output of the neuron. So this is how the convolutional network works. So let's see an example. So this one, the big matrix is the image. The small matrix is the kernel. So the first neuron in the convolutional layer takes this kernel, overlaps it to the top left corner of the image. So basically it overlaps with this portion P that is circled there in red. Calculates the convolution operation that is written here between the kernel K and the portion P. The result is -1, and then -1 becomes the output of this neuron. Then we repeat the same operation for the neuron on the right. The neuron on the right moves the kernel K a bit on the right on the image, overlaps with a different portion P of the image, calculates the convolution, and produces the output. Then we move to the third neuron. The third neuron, again, moves the kernel a bit more on the right, and then again, the whole thing continues. I would like to add here 2 concepts. The first one is that the number of pixels that I use to move the kernel from portion to portion on the image, this number of pixels is called stride. The higher the number of pixels, so the bigger the jump from one portion to the next portion, the lower the dimension of the output feature map from the convolutional layer, but also the risk of losing information is higher. Another trick is the zero padding. Sometimes around the image, the images are framed with a number of zeros, and this zero padding is useful because it helps with the alignment of the image and with the preservation of the spatial resolution. However, of course, the images are already quite big from a dimension, from a size point of view. In the input, if you add more zero, of course, you also increase the size of the input and the complexity, the computational complexity. So let's see what this kernel do. Those are handcrafted kernel, just to show you an example. So if we use this kernel here, the 0 and 1 kernel here, and we overlap it, we use it to process this image with the houses, then the result we can see is the detection of the vertical lines in the image. If in the second case, if we use this kernel with the 8 in the central place, and we use it to convolute the image of this animal here, then we can see that the result is an edge detection. So that's to say that each kernel has a specific role in the feature extraction from an image. And the convolutional layer is going to train its neurons to extract a specific transformation, to extract a specific feature from the input image. So let's see. As I said, the problem with the image processing is always the size, right? In this case, we had the MNIST data set. Those are tiny images, 28 pixel by 28 pixel, only in gray, black and white. So it's a relatively small input image. However, the problem with the image is if you start adding colors, if you make a higher resolution, if you have a bigger image, is always the size. The size of the image can explode quickly. So whatever you can do to reduce the size of the input image and at the same time to keep the information is always, of course, a good thing to do. So the feature map coming out of the convolutional layer already reduces the size of the input image. However, we can do even better and we can use a pooling layer. The pooling layer, the idea behind pooling is that we take areas of the image or of the feature map that we have, and we summarize, we replace these areas with a summary statistic. The summary statistic can be the maximum value or the average value. So as you can see, here we have an area 2 by 2. So we have an original feature map 4 by 4, and then we use replace areas that are 2 by 2 long and don't overlap. And these 2 by 2 areas are replaced by the maximum value using the maximum pooling or the average value using the average pooling. Again, the pooling layers, they reduce the computational complexity because they reduce the size of the feature map, and at the same time, they increase the receptive field for the following layers. So the whole pre-processing the whole pre-processing of the image in a neural network is often obtained by pairing convolutional layer and pooling layer. So as you see here is an example. You have the input layer here. That's a tensor with the 3 matrices of red, green, and blue. Then you have a convolutional layer that is going to extract some features from the input image. Then you have this one is paired with a pooling layer that is going again to summarize the feature map obtained from the convolutional layer. And then you can repeat this operation of pairing convolutional layer and pooling layer together to extract and summarize more information from the input feature map or image. So again, here, for example, there is another convolutional layer, a pooling layer, and then you can have more if you want. At the end, once you have reached the level of pre-processing that is satisfactory for your problem, then you can just, you stop, you flatten the whole feature map into a single vector, and then you proceed with using a fully connected classic feed-forward neural network that Catherine has described before, and you perform the classification using that neural network. So there are many successful examples of convolutional neural networks for image recognition. They are all cited here. The AlexNet was the first one, and then a number of other ones. Those are complex and big neural networks, they've been trained on a very large data set of images. Very likely you will not have such a big data set of images, and you will not have the computational power to train such big networks. So training these kind of networks is a long and complex process and requires powerful machines. And what do you do if you don't have them? So there is one technique, one trick is called transfer learning. So the idea is that I take one of those networks that have been already trained, and they are already ready on some kind of task, possibly a similar task to the one that I am supposed to run. And then I add a few more layers on top of this already existing and already trained network. I freeze all or some of the previously trained layers, and then I retrain the remaining part for my new task. This works surprisingly well. Of course, the closer the new task is to the old task, the easier it is to perform this kind of transfer learning. But let's say that in general, this technique has worked surprisingly well. So this is a relatively accepted technique. So let's see how we implement the classification of images using a convolutional neural network. Here you can see here the input layer. That's the same node that Catherine was using for the feed-forward neural network. Then there is here a convolutional layer. Then we add the pooling layer. You remember they often, not always, but often come in pair. Then we have the flattened layer, and then we have the two dense layers for the feed-forward fully connected network. This is the structure of the network. And then, of course, you feed the structure of the network into the Keras network learner together with the training data. The Keras network learner performs the training of the network, and then the Keras network executor node performs the application of the network. And then, of course, you score the final results. Those are the same nodes that Catherine was showing before for the feed-forward neural network. So the only difference with what Catherine has said before is only in this convolutional 2D layer node and the max pooling 2D layer node. So let's have a look at how those nodes are configured. As I said before, that's the Keras input layer that you have seen before with Catherine, but I wanted just to point out that the shape here is 28-28-1. You remember the images we had to do with, they were 28 pixel by 28 pixel and only one matrix for the black and white. So this is the description of the tensor structure. After that, we had the convolutional layer. The convolutional layer takes as input the values coming out of the input layer. It has a kernel size 3 by 3, and the stride that it defines is 1 by 1. So that means that the kernel size, the portions of the image that each neuron explores, will overlap quite a bit. The option valid for padding means that there is no padding. There are a few other options to introduce the padding, and then we have 32, which is the number of different kernels that are going to be trained and applied. Then there is the pooling layer. The pooling layer has a pool size 2 by 2, and the strides are 2 by 2. So that means that in this case there is no overlapping of the different areas explored by the pooling node. And then the last one is the flattened layer. The flattened layer, as I said before, only takes the image and flattens it into a single vector. So there is really no special settings that you're supposed to apply here besides the input, besides choosing the input tensor to the node. Okay, and then we move to the Keras network learner. The Keras network learner takes as input the image, takes the image as input, produces a one-hot tensor encoding of the numbers that are proposed at in the training set for the target, and then uses the ADA delta and the categorical cross entropy for the training. So how well did this relatively simple network do in classifying the MNIST data set? So as you can see from the scorer node, at the end we had a 94% accuracy with a 5.7% error. So it's actually not bad. It's pretty good actually. So it's I mean, for the relatively simple architecture, it didn't perform badly. So can I improve this performance? Can I add one more convolutional layer, for example, and see if this performance improves a lot? So another network that we have that I found on the KNIME Hub includes one more convolutional layer. So as you see, the structure is exactly the same, but there is one more convolutional layer here, and then there are a few dropout layers in between. The dropout layer, they don't really add much to the architecture because they are going to be removed after training. They only add the randomization during the training procedure that guarantees the network from the overfitting effect. So let's ignore for now the dropout layers, but so the other layers, the other differences in the architecture is only in the one more convolutional layer. So how was the result? The result ends up being an accuracy of 96% and an error of 3.7%. So there is a 2% improvement in the accuracy. Was it worth it to have one more convolutional layer to have 2% more accuracy? I would say it depends on the problem and on your tolerance to error. So, but that's the kind of improvement that you would get on the MNIST data set. Okay, so I finished now with the presentation. I would like to give you a few links to the workflows on the KNIME Hub. This is the link to the workflows that the workflow that Catherine was building. This is the link to the MNIST classification using only one convolutional layer, and this is the same MNIST classification but with two convolutional layers. So all these workflows are available on the KNIME Hub. You can download them. You can you can work on them, change them. You can do whatever you want and improve them. And then I would like to remind you that on March 24, we will have the KNIME Data Talks. Registrations are now open. The KNIME Data Talks is they are 3 hours in the afternoon in Europe, and so there will be many different presentations. I would like to remind you that so that means I and Catherine and 2 more experts in deep learning here at KNIME, will be running a panel discussion. So if you have some burning questions about deep learning that we haven't answered today, that something that you would like to discuss a bit more deeply, come to the panel discussion at the KNIME Data Talks.
One question is whether you can make your own kernels and view the resulting images in a node. And do you want to answer this one, Rosaria?
Can I make my own kernels with the resulting images in a node? If I can.
So normally with your own kernels, you normally don't define the weights on your own. So you don't define the kernels on your own, but this is actually the weights which you train during the training process. That's why you normally don't define your own kernels. And whether you can have a look at the resulting images, that's something I've never tried.
You need probably, so if you, so you cannot define your handcrafted kernels. For the images, there is a image library, and but you need to do some transformation. It doesn't come out visible out of the network executor node. Any support on Android platform where one can deploy the model on Android devices and use it during inference phase at real-time scenario? This is a deployment question. Mm-hmm. We have seen the node, the network executor node. So in this one can be used for deployment. We can, so whatever workflow you build for the deployment of the network, you can of course develop it as a REST service, and you can call it from an Android platform. That's of course possible. It involves calling a KNIME server rather than the KNIME Analytics platform, but that would be possible through the KNIME server, yes. Is there a promo code for the L4 deep learning course? Catherine, this is for you, I think.
So for today, we haven't prepared a promo code for the L4DL course. No, we have already a lot of other promotion codes today.
Is performance speed using the Keras KNIME integration similar to using Keras from Python? Is it much slower? It's not slower, is it?
It's a bit slower because we have to send the data from KNIME Analytics platform to Python because our Keras integration is based on Python. But what you can do during deployment is that you can convert your Keras model into a TensorFlow model, and then we don't need this intermediate step of sending the data from KNIME to Python, because then we can actually use the Java library to call the TensorFlow model.
So another question is about the promotion code for Amazon. I think it works also for Amazon.co. So for all Amazon, I think. We can come back to you with the answer to that. Do you know, Catherine, if it's working for all Amazon? I think so.
It should, and if it does not, then please reach out to us and I can try to get this solved.
We can copy the links in there. Okay. I will stay 5 minutes longer and I'll copy all the links in the chat.
But you will also receive all the links with the follow-up email afterwards.
This is true. You will get that if you register. Yeah. So this one, the question about the Android platform and the API support. We have some examples. Do you want to send us an email and then we can send you a bunch of links in the example? If you go onto the KNIME Hub and you type REST service, you should find a number of examples. But if you want to have you have some more specific questions, then maybe you should send us an email. You can try to send us an email at education@knime.com.
Then there is a question whether we will share the videos and the slide deck. And yes, we will share the video and the slide deck with the follow-up email.
Okay, so the person who wanted to have the links copied there, is that okay if we send the follow-up email with all the links, or do I have to type them here now?
And answering Alberto's question, whether you can define the architecture and send it for training to the cloud. And yes, you can train neural networks in the cloud using KNIME Analytics platform, because on, for example, AWS Marketplace, you can find KNIME Analytics platform on the AWS Marketplace, and then you can there select a machine with GPU support, and then train your neural network on AWS using the GPU support.
If there are no more questions, then we will send you the follow-up email, and thank you for listening.
Thank you everyone for joining, and have a nice evening.